Newton's gravitational force law tells us, well, let's write it out first, and we'll see what it looks like. Force is equal to big G, mass 1, mass 2, all over r squared. Now, big G is called the gravitational constant, and it is equal to 6.67 times 10 to the minus 11. It is very small. That is very meaningful. What it's saying is that the force of gravity really is very, very, very weak. But when we are working with a mass as big as the Earth, and the mass as big as the Earth is 5.98 times 10 to the 24 kgs. Good idea to get used to these numbers. Radius of the Earth, 6.3 times 10 to the 6 meters. So this is mass of Earth, radius of Earth. Now, what is this force law telling us? What it's telling you is the force between two objects. Now, as usual with Newton's third law, the force between two objects are equal and opposite. So when you're sitting on a planet like Earth, or not sitting, standing, whatever you want. So I'm standing here like this. Then my weight force is equal to, as we've done for many years now, mg. That's the force of gravity. All right. Now, we've always done it that way, and we've said that our weight force was a force and it was in newtons. We've looked at little g and we've said that's our acceleration. It all seemed a little bit, well, it seems pretty normal now, but it all comes from this equation here, and we've got to see how that happens. But before we move on to doing that little bit and that calculation, what we need to realize is that there are two forces here. Even if I'm jumping out of a plane and I've got this weight force, which is the gravity force, pulling me down, then where's the equal and opposite force? The equal and opposite force is acting on the Earth. So the Earth pulls on me with a gravitational weight force, and I pull on the Earth. So I accelerate towards the Earth, and the Earth accelerates towards me. So the Earth does move when I jump out of a plane. Only a teeny little bit, because its acceleration is very small, because as we all know, force equals mass times acceleration. So if my weight force is 700 newtons or whatever, then if I divide that by my mass, I get my acceleration. But if I put in the Earth's mass for that 700 newtons, I get this real teeny little bit of acceleration. So, but it's important to understand the principle of equal and opposite forces. And with Newton's third law, the equal and opposite forces always act on different objects. Very important to remember that. So what's mass 1 and mass 2? Well, there are two masses involved when there's a force between two objects gravitationally. So I often like to think of mass 1 as the big object and mass 2 as the little object. So when we're looking at this, and we put in these numbers, if I put in the mass of Earth there and the mass of the object, then if I'm wanting to know how fast an object accelerates, right, then all I do is divide by the mass of the object and I've got its acceleration, right? So if I know the force on the object is the gravitational force, and m2 is my little mass, and I've just said that if I know the force and I divide by its mass, and I said it was the little mass I was interested in, then I divide the force by the little mass and I get the acceleration. So if I do that over here, then the m2 cancels, and we find out that the actual acceleration is equal to big G, big M1 all over r squared. Now if you put those numbers in, what's big G? 6.67 times 10 to the minus 11. Big M, mass of Earth, radius of Earth squared divided into, then believe it or not, well, I know you do believe it, we'll come up with the acceleration of 9.8 meters per second to the minus 2. So that's Newton's gravitational force law.